out of this. And I've got L and L squared from here, so I have L to the power 3 in the denominator. I'm left with Vx1 squared plus Vx2 squared all the way up to Vxn squared. Okay, good with that? Again, there are a few steps here, but all of them are pretty simple intrinsically. So I know the pressure now is force over area. Got this. Now I need to say something about this term here with some averaging. So we are going to average. We have a large number of molecules, and so we can take instead the statistical average of speed. Replace this, and I'm just going to also note that we know that n equals little n, the number of moles, times Avogadro's number, all this into the next step. And what I should get is, let's see, pressure equals m over L cubed, little n times Avogadro's number times now the average of the Vx squared for all of the constituents. Slightly didn't do this with the best use of space, but it'll still work because I think I've got everything on here. Let's go from here down to here. What else do we know? A couple of other substitutions. We're almost there. Once it's all there, I just want you to look at the whole derivation and then ask me questions. So we substitute also the following, and you can see I'm needing to follow my notes carefully here because I usually get lost with these substitutions. L cubed is the volume. This is the molar mass. We talked about that last week. So we substitute also for those two things, and what we get is the pressure is N times the molar mass times the average of the x squareds over V. We're almost there, okay? Last thing I'm going to do is say something about this average. This is still obviously in terms of the x component of the velocity, because that's all we've been dealing with. What I'm more likely to know, of course, is just the velocity, the speed, if you will, of each molecule. So what I'm going to make use of here is the fact that the molecules are moving randomly in 3 dimensions. That's important. Random, again, large volume, large number of molecules in 3 dimensions. And here's the bit that you might be a little less comfortable with, so I just want to pause and talk about it. Okay, so here's the thing I just want to pause and talk about. So they're moving randomly in 3 dimensions. Obviously the velocity of any individual molecule is made up of the quadratic sum of each of the components, Vx squared, Vy squared, Vz squared. And so again, on average, or at least for looking at this for a large number, we can say that Vx squared is 1/3 of V squared. Okay? So this is the thing that maybe just requires a little bit of thought. If you admit that, then we are pretty much close to where we need to be. So let me do this down at the bottom. E now equals N M V squared average over 3V. So my Vx squared average has been replaced by total V squared over 3 because of this. And this, lastly, is what we call the root mean square speed. Okay? So, hopefully we're all familiar with root mean square definitions. I take a statistical distribution of something, whatever the quantity is. I square it. square this, take the average, and if I was talking about the root mean square, I would square root that, but in this case we've got the RMS squared. And so finally, and I know this has been a little bit of a tedious slog, we end up with this. And timing is going to be not too bad, because we need to talk about it a little bit. Okay, so that's what drops out of this. Let's look at the answer, see what physical intuition it brings us. I'll show you a quick demonstration, and then pause for asking questions, and I think I'm going to stop there. This is the end result. What have we done? We had, for this set of very simple assumptions, idealizations, for a certain volume of gas, depending on how much of it we have, it turns out what type of gas is important, what its constituents are, because we're worried about the particle momentum, so obviously the mass is important. So for a given gas, given amount of it, given volume, given the type of gas, these things are all constants. So the only thing that's left is a direct proportionality of the observed pressure, let's say on the container walls, goes as the square of the mean square. The square of the velocity, basically, of the constituents. Okay? So this is what this has given us. It's given us a connection between macroscopic and microscopic. Again, very simple inputs into this, stuff you already know. And this is going to turn out to inform a lot of our understanding of the behaviors we talked about, plus of course a lot more. Let me show you one demonstration, and then I'll pause for questions, and I think we'll stop. So, kind of silly, but as good as anything else, try to demonstrate at the bottom of this plastic transparent tube are a bunch of kind of little marbles. On top of them is some just kind of cover, basically. And so the marbles right now are sitting within whatever volume they want to sit in. And of course this is a macroscopic demonstration, so in fact they do have close to zero velocity right now, and never get through at the microscopic level, that's quantum mechanics. All I'm going to do now is start giving these constituent marbles, in this case, some kinetic energy. Okay. They're getting some energy by having the base of their container be vibrated, but that's getting some momentum. In part, they're starting to jostle around. If I increase the amount of energy that's imparted to them, increase the velocity, of course, they're moving faster. And as they move faster, the pressure that they exert increases. In fact, it goes 1 over the square of the speed. This is what's going on in your kinetic theory model of gases. I give them more and more energy, and the pressure is increasing. In this case, the pressure is increasing in the inside from these marbles, pushing up more and more against the ambient atmospheric pressure. So the top of this container is rising. The volume is increasing. In fact, maybe if I go far enough, this one's quite off. I don't know. Okay. I'm not going to do it. This is the image I want you to have of gases, ideal gases. Okay. Time for just a couple of questions on this. Yeah. The question was just to go over this, okay? So, we're only looking at this molecule which has components of velocity and all coordinate. We're only caring about its collision with the right-hand wall. So just think of this in terms of an elastic collision. I've got a rigid wall. This thing comes in, and its x component of momentum, which is all I care about. It's the x component that's actually going to be inverted when it bounces off. Y and z components won't change. So it's the x component, and this is just delta. So this is the final momentum minus the initial momentum. And in this case, it's coming in the way I drew it. It seems to be moving towards the right-hand side. I'd set this up implicitly with the plus x being positive. So the initial momentum is plus mv x. It's an elastic collision, so it bounces off the same velocity as it's going out in the minus vx direction. So final momentum minus mvx minus the initial momentum, I get this, and these are the magnitude. Yeah, Ariel.
How exactly do you find this square velocity?
So we'll talk some about that. What do we have? Thursday. We'll talk some about that on Tuesday. Basically, we're going to use it as simply probably the most statistically relevant parameter for a large assembly of molecules. So we're just going to say, okay, we've got this very large number of molecules. Yes, they have different velocities. But we're just going to use this statistical definition of RMS, moving square velocity, and that's all we're going to use to define the speed. When you say, how do we find it? Do you mean, how do we experimentally know what it is? Or
How, like, you know, given the velocity and what would that percentage do if we didn't see that velocity?
So usually, again, there's going to be some distribution of speeds, and we will talk about this on Tuesday because we'll look at that distribution. But for us, more often than not, everything we care about will simply be in terms of the RMS velocity. And quite what the distribution looks like, we won't in general care much about. So you'll probably just be working solely with that parameter. Any last questions? Yeah?
So this formula holds for any volumetric shape, even though we go back and forth?
Correct. Yes. This is obviously a simplification with this geometry, but yeah, holds for any volume we take. All right, we're good. Somebody could turn the red button off on the camera, that would be great. Stay tuned for hopefully an office hour tomorrow, likely afternoon, if it happens. Otherwise, everything else